My objective for today is to give you enough information for us to all comfortably get started in the lab this week. And on that note, make sure you decide on a lab partner and send me an email with, or at least one of the two members of the group should send me an email and give me both names. If you're not sure who you can partner with, let me know that too, and I have a list of students who are looking for a lab partner, and I'll try to pair you up. Okay, so last time, whereas the last lecture was more, turn this on. The last lecture was more introductory. This one's going to be more technical. I'm going to try to give you all the information you need to get started in the lab this week. So last time we talked about the ATmega processor that we're using in class. It's a really lightweight 8-bit processor. Basically what it's got is, in terms of being able to control things, it's a microcontroller. This has got 22 general purpose I/O pins that can be used for input or output. And that's for things like 7-segment displays, push buttons, LEDs, simple components that you want to directly be able to communicate with through an arbitrary binary interface. Then it also has hardware support for 3 standard protocols, which you could think of these as kind of like languages. And so there's a lot of peripherals that can speak, most peripherals designed for lightweight embedded systems can speak one of these 3 protocols, one of these 3 languages. There's a SPI, I2C, also called TWI, and UART. And so there's hardware support. The chip has hardware support for enabling those protocols. And I'll talk more about that in a minute. It also has a pulse width modulation, has hardware support for pulse width modulation, which is kind of like a fake analog output where you still have a binary output, but you have a kind of a periodic binary output where the duty cycle, or the percentage of time, the portion it spends at VDD as compared to ground, can vary to simulate an analog signal between 0 and 5 volts. But it also has real analog input within, through an analog to digital converter. And then it also has interrupt pins that can be used to interrupt, for external peripherals, external components to interrupt the processor when they need attention. So this is basically, the whole class is really designed around these concepts. We mentioned that the chip physically has 32 pins, and I gave you a pin map that attempted to map out what the pins on the board, how they match up to not only the pins on the chip, but also what each of the specific special purposes each one of those pins has. Charles has also created this really nice alternative diagram that shows that. So he kind of has an outline of the board, and it shows the 4 headers. And for each one of those, he's actually got the pin number on the chip, which is 1 to 32, because there's 32 pins, 8 pins per side, there's 4 sides. And then also, there's these, I mentioned last time, when you're doing GPIO, they have 3 GPIO ports, 2 of which are 8 bits and 1 is 7 bits. I don't know why they do it that way. So you get 23 bits in total that's spread across port B, C, and D. So if you see like PD6, that means bit 6 of port D. But then you can also see that particular pin also can be used for analog input 0. So that pin is also connected to the internal analog digital converter. And it's also used for, there's 2 other, I don't know what, OC0A, it looks like one of the oscillator pins. So you can see that each one of these pins can have up to 4 purposes, 4 things you can use them for. Yes?
Are PWM pens computationally expensive?
No, well,
less of those than digital?
They would be if you were doing it in software. So if you were writing code, that was having to set the PWM pin, it could be expensive. There could be overhead, software overhead. It takes instructions, and it would have to utilize the processor to do that. But the PWM, and you can do that. You can still do that. That's called bit banging. That's when you write software to achieve some behavior on a pin, I/O behavior. But the PWM, there's hardware PWM, where basically you use the software just to configure the hardware, and then it takes over and it works concurrently. So it will drive the PWM in parallel. So that way you don't have to use time. You don't have to use instructions to create that, to perform the PWM or to output the PWM. It goes by itself. Okay, so I mentioned last time about programmed I/O. So all of this stuff, setting up these hardware devices or doing GPIO and having the software interact directly with the pins, is done through programmed I/O. So there's this idea of a status register, which are flags that are in a register that is visible by to the software. So the software reads a register, or actually it's reading a memory location, because each one of these registers is mapped to a memory location. So it reads a memory location, and then each of the bits in there has some special meaning as defined in the user guide or the data sheet for the chip. And they're used as flags. So you can think of those as input bits. And then there's a control registers, which are used to control external peripherals. So you can think of those as output. I always think of status as input and control as output. But I found in this chip, it's a little confusing because they tend to mix status and control bits together in the same register quite a bit. So you'll find that there's a lot of bit twiddling you have to do, in the sense you might have to extract one bit from a register as an input, but then drive another bit in the same register as an output. So they do a lot of that. It's actually a little awkward sometimes, but you have to kind of, it requires that you're looking up the definitions of what each of those bits is for in each one of these registers. So there's 64 registers specifically in this chip that are used as status/control registers. I think they call them I/O registers, right? But basically, there's 64 8-bit locations that are used to control and monitor hardware. So how do we do this bit twiddling in software? This is this example I showed last time, where in general there is a header file that is provided to you by @Mega, and it contains these pound define, which in C is just a way to set a constant. And they have a pound define these constants for each of the registers. So each register has a name that you can refer to in your code, as well as each of the bits in all the registers. So you've got a name for each register and a name for each bit. So that way, if you want to, for example, if you want to set the halt bit, so we have a register which I just gave an arbitrary name of PNTLS. Sometimes it's obvious what these mean, other times it's not. A lot of times they could be an acronym or a shortened version of the name. But in this case, if I want to set the halt bit, which is bit 7, I don't actually have to worry too much about the address of this register, where it is, because every register has an address between 0 and 63. I don't have to worry about that because I can refer to it by its name, and the bit halt, I can refer to it by its name. So I can say PNTLS equals, and because it appears on the left-hand side of an assignment, it means I'm setting it. But I only want to set the halt bit to 1. I don't want to mess with the other bit. I don't want to modify the other bits. I don't want to contaminate the other bits. So so in order to do that, I also read the existing value of the PNTLS register by having it appear on the right-hand side of the assignment, and then I use a bitwise OR. And then I take a 1 and I shift it by halt. So obviously in this case halt is 7. But I don't want to have to worry about putting a 7 in there. I just use halt. So it takes a 1, it's going to shift it 7 bits to the left, and then it's going to OR it into there, meaning that it's going to set that bit to 1, or if it's already 1, it won't make any difference because 1 ORed with 1 is just still 1. But it's going to set halt without modifying the other bits. Make sense? right? It's using this bitwise OR. Likewise, if I want to set halt to 0, or if it's already 0, keep it at 0, then you can do something similar. Use a bitwise and you still take 1 and shift it left by halt, but you use the tilde here that does a bitwise complement. So it's like saying, I want to AND the existing value of the register, I want to AND with all 1s, except for a 0 that I want to put in the position of the halt bit, right? So it'll AND just bit 7 with 0, right? With a bitwise AND. So this will set it to 0. You could make a macro for this. Probably a better way to do it, although the code we've been writing, we generally just do it this way, to set and reset a bit. So you see a lot of that. And then if you want to read a bit, like if you want to test to see if a bit is set, you can just do a bitwise AND with 1 shifted by, in this case, on fire. We're checking to see if the on fire bit is set, and that's going to give you that is going to result in either a 0 or a or 64 numerically, because halt is on fire is bit 6. So if that was set, then the result of this expression would be a value with bit 6 set, which would be a numeric value of 64. But in C, 64 would be true, right? Because in C, any non-zero value is considered true and 0 is false. So if you were to take this and incorporate this into like an if statement, then it would just be true if it was set and false otherwise, right? Any questions about that? Okay. All right. So the I/O ports, I mentioned there's 3 I/O ports. Each of the I/O ports has 3 associated control/status registers. So I mentioned there's B, C, and D. I don't know why there's not an A. So there's port B, port C, and port D. And so for each of those, there is a DDR. So DDR-B, DDR-C, and DDR-D, right, where the X here is the A, B, C, or D, as well as a port BCD and a pin BCD. So the DDR is the data direction register, and this just allows you to define which bits in each of the 3 ports you want to be an input and an output. So if it's a and you can read and write to that register, but it's designed to be written to primarily. So you can configure each of the ports to be, or each of the pieces of the ports, each of the individual bits of the 3 ports as inputs or outputs. So if you set a corresponding bit to 1, it is a output according to this table, and if you set it to 0, it's an input, but there's different ways that the input has different modes. You can, which we'll get into more later. There's also a port. Now, if you're configuring if you have a pin that you're using as an output, the port is just what you're outputting on that pin. So it's real simple. The port's just your output. That's what you use to send a signal out of the chip to drive a corresponding pin to 1 or 0, you just set it in the port. So if I want to use bit 6 of port B as an output, I would set it to that bit in that DDR-B, bit 6 in DDR-B, I would set that to 1, and then in port B, bit 6, I could set that to 1 or 0, and that would define what the chip is emitting on that particular pin. On the other hand, if I'm using the pin as an input, then the port is used as a secondary configuration bit to determine the mode, whether the pin is in pull-up mode or not, for the input. Right? And then also, if it's an input, there's a pin BCD that you read to retrieve the input value. You guys with me? So you can set up the pins to be inputs or outputs, and when I say pins, I mean the 23 pins that span ports B, C, and D. You can set each pin up as an input or output. If it's an input, it could be pull up or not. And then if it's an output, you just set port to use the output. If it's an input, use port to set the input mode, and then pin to read the input. Yes?
Is this something that's done like at the beginning of the program?
Yes. Well, it could be either way, but yeah, you could set, like, for example, your code might have an initialization section that sets all this up, or You could change modes halfway, while you're running. I think it's most common probably to set things up at the beginning. So every program will have its own, we'll set it up one way at the beginning. It's probably, I would guess it's uncommon to change the GPIO setup, midway, but it's possible. Okay, so let's look at an example of how you do this. So I wanted to come up with a way to do hello world, but I didn't want to print hello world. I wanted to send hello world out on one of these GPIO pins. So you start out with include io.h and include string.h. Now string.h is a standard POSIX library that includes string-related functions like strcomp and strlen and that kind of stuff. Hopefully, I don't know if you guys use that in 240 or not. Maybe. C++ has its own way of dealing with strings. Yeah, this is a string.h is kind of a C, the C library for processing strings, or doing basic string processing, or handling, I should say. The AVR/io.h is specific to this board. And this is the header file I was telling you about that has the constants, the symbols defined for the I/O registers and the bits in each I/O register. So I create this string. I declare and initialize a constant string that says hello world with 2 spaces after it. And I do that as a global variable, and I know it's global because it's outside the scope of any function. And then I have a main function. Every C program needs a main function. That is what's run when you execute the code. And in there I declare a uint8_t len, and then that is essentially a constant. It's a variable, but it's storing the length of string. You see that? So it's a constant, meaning that it can't be changed once it's set. The type is uint8_t, which is an 8-bit unsigned integer. And it's initialized to whatever the length of the string is. Now you might say, well, the string's a constant, so the length should be constant. Yeah, but the idea is that you could then change this string, and then the length would adapt to that next time you compile. The problem with this, of course, is that this wouldn't work if the string is greater than 255 characters. So this is kind of a toy program. The assumption here is that this string is relatively short. And then I have this I have an I variable, also an unsigned 8-bit integer that I initialize to 0. And then the next thing I do is set up the DDR-D, the data direction register for port D. And I just put a FF in hex, which sets all of the 8 pins of port D to be outputs. And then there's a while loop that sets port D, which is the output value, to string at I, and then I increment I, and I modulo it by length, so it'll go from 0 to the length -1, and then back to 0. So it'll just constantly go through each of the characters of string and then repeat, right? And because that port D assignment is being done in the while loop, that's what's actually putting each of these characters out, right? So the string, now it's a little misleading because I declared the string as a char. So the assumption here is that a char is an 8-bit value. So each one of these characters should be able to fit on the 8 bits of the D port, right? So I'm going to take each of the characters of the string and blast it out of port D once per iteration of this while loop. Make sense? So sending each character out is done by this assignment of port D. Okay, so then how do we actually hook up the board? So I got some pictures here that show this is the board. Now actually, these pictures are a little out of date. This is when I took these pictures, I was using an Arduino Uno. The boards we use in class are a little different. The headers are all the same, but the chip is smaller, and the board is not green, it's black. So I hooked up, there's a logic analyzer that we're going to have in the lab. Each lab station has a logic analyzer, or actually has an oscilloscope that has an internal logic analyzer. And so what is a logic analyzer? It's a way that you can read binary data in parallel buses. So there's these probes that have eight wires coming out of them. There's a probe, you plug it in logic analyzer, and it splits off into two 8-bit buses. So there's 16 bits in total. But each one of these little black boxes that split off have eight wires each. And I just plugged each one of those into each of the 8 ports of port D. Now, how did I know what port D was? Well, the only way to know that, I mean, it's kind of funny, you know, you would expect it to say it on the board. It doesn't. It doesn't say port D anywhere on the board. You would never know what port B, C, and D is by looking at the board, the silkscreen layer on the board. It's completely ambiguous. All it says on the board is digital, and then it has numbers, some of which have tildes. That's not explained. Just who knows? But if you look at either one of our diagrams and you match it up to the board, you can see that this header that's in the lower right-hand corner is actually port D, and all 8 bits are there in a line, with the least significant bit being at the bottom, and as you go up, you go 0 up to 7, right?
Just remember, like PD, PB, etc. are shorthand for port D, port B.
Right. Yeah.
If it says PD1, that means port D1. I just don't want to make it like super wide.
Yeah, I mentioned that. I use the same notation in my table too. So in my diagram, I had this yellow box that highlighted those. So both of these slides are showing the same information. They just present it in 2 different ways. Without these slides, the only way to know this is to you have to go to the board design, actually, because even you wouldn't know this even by looking at the data sheet for the chip, because this is a board. This depends on how they design the board. Right now, all Arduino boards are standardized, but you still would have to find a board design to figure that out.
Buried on the manufacturer's website, there was like a quick reference diagram. It's somewhere in the resources folder. It's one of the JPEGs. It's pretty crappy.
Yeah, we're going to put, I have this one in the slides, and I'm going to put Charles's PDF of that as well on the website. Okay, so anyway, so I know port D is down here. Why did I pick port D? I don't know. I could have picked, port C only has 7 bits, so that wouldn't have worked so well, but I could have picked port B. But anyway, I picked port D. I plugged the wires in. They're color-coded according to the bit, so you have to put them in the correct order. This thing is then plugged into the logic analyzer right in the middle on the bottom. And then once you've got that plugged in, you hit the bus button. So the logic analyzer has three analog channels, right? Is it 3 or 4? 4. There's 4 analog channels that are labeled A through D, I believe, right? A through D, or maybe 1 through 4, one of the 2. But that's just the analog channels. If you want to do the logic analyzer, you want to use a logic analyzer, you want to use digital, then you have to use these the bus buttons. So I've got this plugged into bus 1, so you hit the bus 1 button. And once you hit that button, the side buttons will give you some options. So you can set up the number of data bits as, I'm going to say 8. Now, how do you change that? Well, notice that there's this A. This letter A actually matches up to a dial. I don't show it on here. You can kind of make out the B dial here where it says multi-purpose B. But right above this, there's an A dial. So you can adjust this with that dial. But it probably will come up as 8 by default. So you configure it as an 8-bit bus, and then down at the bottom of the screen, this is the side of the screen, on the bottom, you can hit the bus display button. And in this case, I set it up as hex, because I wanted to see the hex digits. I wanted all 8 bits to be grouped into 2 hex digits. And then you hit the menu, the trigger, yeah, so you want to set up the trigger. So I set up the trigger, I hit the menu button under trigger, and then I set up the trigger to be 48. Why? Because 48 is the ASCII code for capital H. So I wanted it to trigger on capital H, which is the first character of my string. Trigger meaning that's when I wanted to start seeing it plotted on the scope. And then after that, I just hit single, and then I ran the code, and then you can see it actually. You can see on the screen you have the HELL space world, but in order to figure that out, you have to look at the hex table, right? Because there's no way. I thought the scope would automatically decode ASCII characters, but it doesn't. So, but you can just see them on there. You just have to translate them through an ASCII table. This is from ASCIItable.com. You guys with me? You all know ASCII, right? Okay. Okay. All right. So that's GPIO. Well, that's output. Doing GPIO with output. I haven't shown input yet, but I want to switch gears here and talk about USART, or sometimes I call it UART, UART or USART. USART stands for Universal Serial Asynchronous Receiver Transmitter. This is a standard protocol, low-speed protocol that's used oftentimes for console I/O, like a text terminal. It's very simple. It consists of 3 physical wires that connect 2 endpoints together. As far as I know, you can't have more than 2 devices on a UART bus. It's a point-to-point type connection. So that way you don't have to worry about arbitration.
You can have multiple readers, so you can do like a broadcast setup. Like if you just connect the same TX pin to several RX pins.
Oh yeah.
It will work. Now you can cause signal integrity problems if you put like too much impedance.
Right, but if you want full duplex.
Yeah, if you want full duplex.
There's 2 hosts, yeah. So this is a full duplex. You can do full duplex, meaning that you have a 2-way communication between these 2 hosts. The advantage of that is you don't have to worry about arbitration. You don't have to worry about two hosts having to share the same physical wire and then having to worry about what happens if they both try to talk at the same time, right? So basically, there's just a transmit pin and wire and a receive pin and wire, and then there's a ground. Yes?
Does one transmit not go to the other's receive?
It should, yeah. Oh, yeah, you're right. That's mislabeled. Thank you. Sorry. Yeah. That should be receive. A transmit should go to receive. Receive should go to transmit. Yes, thank you. So one of the things about UART that's a little problematic is that it's asynchronous, meaning that there's no clock signal as part of the bus wiring. So each of the endpoints here have to agree somehow on the speed, on the bit rate. Which kind of stinks, because if you buy something off the shelf and it has a UART port and you want to plug into it, you have to like figure out what the speed is, otherwise it won't work. And oftentimes that just involves trial and error, unfortunately, or unless you can read it off the the instructions or something. But who reads instructions? So basically, the format is it's just you take it's a sequence of bytes, 8-bit byte, generally 8-bit bytes, and you serialize them. So you have an 8-bit byte and you want to send it across a 1-bit wire, so you just send 1 bit at a time, right? And it goes from least significant to most significant. So you're essentially reading the bits of a byte from right to left. Now, there is some synchronization involved. So normally when the bus is idle, the bus state is a 1. So like if you have a UART bus or UART pin, transmit pin, you'll look at it, you'll see there's a 1 there. And so in order for the transmitter to signal that it wants to start a transmission, it wants to send a byte, it puts a start bit, right? Well, the start bit is active low. So the bus is normally high, and the start bit is putting a 0 on there for one bit time, and the bit time is determined by whatever speed you're running the bus at. And then from there, you send each of the bits over from right to left, and then Generally, there's the stop bit is a 1-bit time where you return the bus back up to high state. Now you can also have a parity bit optionally that's used for error detection. So depending, if you have the bus configured for having a bit of parity, the parity bit would come after the most significant data bit, but before the stop bit. And then obviously the parity indicates whether there was an odd or an even number of ones. So yeah, the odd parity is it's high, it's logic high if the data contains an even number, and it's even if the data byte contains an odd number, which seems counterintuitive, but the idea is that if you have odd parity, you want there to always be an odd number of 1 bits, including the parity bit. So if there was an even number of bits in the data, then you put an extra 1 bit to make it odd. Does that make sense? And then likewise with even. So if you have an even number of, if it's even parity and you have an even number of bits, you have an odd number of bits, then you assert the even parity symbol high. That forces it to have an even number of 1 bits. And then the baud rate is the transmission rate that you're sending these the data at. Okay, so how do we use the UART on this chip? Well, one way is to use the GPIO. You can write code that will use the GPIO pins. You only need 1 of them to transmit and 1 to receive. So in 2 GPIO pins, you remember you got 23 pins, and with 2 of them you could implement UART, or your other option is you can use the built-in UART. If you use the built-in UART, it is going to always use 2 of the pins, which are TXD and RXD, which are the 2 pins that are in the lower right-hand corner of the board, which also correspond to the 0 and 1 bits of port D. So that obviously means that you cannot simultaneously use all 8 bits of port D, as I did in my example, as well as using the hardware UART, because you'll have a conflict there, right? If you tried to do that, it would actually, things would work, it wouldn't blow the chip up, but the UART would take priority over your GPIO. So the minute that the hardware UART started to work, it would simply take over the low order 2 bits of port D. And you say, oh, how do you know that? How does that work? Well, it's actually part of the hardware design of the chip. It actually happens, they have this design in the data sheet, and it's actually happening through this MUX right here. There's this MUX that has one of the inputs is the GPIO that's coming from the port value, the port register, and the other one is this PVO-VXN, and if you look up what that is, it's whatever the specialized purpose of that pin is, which in this case would be the UART. So the chip would automatically switch this MUX up to the top input, and it would override your GPIO. So, like I said, it wouldn't cause any problems, it wouldn't break anything, it just would, the specialized features always take priority over GPIO. Now on input, on the other hand, if, for example, you were trying to use port, I don't know, maybe this is too far in the weeds, but if you were receiving data on the hardware UART and you was treating that pin 0 of port D as an input, you could monitor, like you could still read it, so you would be reading whatever the UART hardware was doing. You could have the software read it. I don't know why you'd want to do that, but you could in theory. Okay. All right, any questions about that? That was a really quick introduction to how to use the scope. Charles and Philip will have more information on the scope when that becomes relevant in the labs. That way you'll actually be sitting in front of it. Okay. Okay. So how do we use the UART? You basically just initialize it, and then you use it by setting characters into a register to send and reading characters from a register to receive. So to initialize it, you have to set the baud rate, you set the frame format, you enable it, and then clear the global interrupt flag. Now I'm gonna actually run through this pretty quick because we actually give you some code that does this for you, but I'm gonna explain it just so you know what's going on in there. So there is a control register called UBBRN, which is used to set up the speed. In all of the projects we've done so far, we've used 57,600 baud, which is 57.6 kilobits per second. They call it baud instead of kilobits per second because the kilobits per second is a little misleading because there's, you've got the start bit and the stop bit and the parity bit, so there's some overhead. So you're not actually getting 57.6 kilobits per second throughput of data because the baud, the baud is the how fast the signal switches physically, including all of the overhead bits that are required as part of the protocol.
If you want to be really pedantic, not that I would ever do that, baud is specifically defined as symbols per second, not bits per second. So something like the stop bit might be a symbol.
Yeah, well, that's what I'm saying. Yeah, it's including all of the overheads of the protocol. It's the rate at which all the bits are set.
The official definition, it'll say symbols is in the numerator.
Yeah, so symbols per second inclusive of all the overhead characters, all the overhead symbols or bits. Okay, so so there's an equation you have to use to calculate the baud rate, and basically what you're doing is setting up the speed relative to the clock rate of the chip, which in this case is 16 megahertz. So basically it's going to be whatever the F oscillator is, which is 16 megahertz, divided by 8 times, let's see, what is it? Actually, sorry, asynchronous normal mode. Yeah, you said, so this is the one we use, asynchronous normal mode. It's the oscillator, the clock frequency divided by 16 times baud minus 1. So, and the minus 1 is after you calculate this ratio. So in this case, it's 16 million divided by 16 divided by 57,600 minus 1, right? So instead of just multiplying these two things in the denominator, you can just divide twice. Make sense? So that is the UBRR, and that UBRR value is set into this register UBRR 0, H, and L, which is the high and low side. So that's a 16-bit register. And then, so that's UBRR, so that's basically the baud rate register. And then there's a control register called UCSR NA, and there's flags in there. Actually, there's 3 control registers. This is the first of the 3 A. There's A, B, and C. There's flags in here that indicate whether the receive is complete and the transmit is complete. So these are used to synchronize the software with the transmission of bytes over the link. There's an error flag and a parity error flag and things that the software can check. This is the B, the UCSR B, so this is the second of 3 control registers. These control interrupts, which I'll get into in just a few minutes. I'll talk about interrupts. Character size, so this is setup stuff, initialization stuff. And then finally, control register C allows you to set the parity mode, the number of stop bits, the character size, and so on. There is a way to actually do 9-bit characters, but we haven't tried that. We always use it in 8-bit mode. So basically, there's no way to, generally you're not memorizing this stuff. You have to check the user guide, the chip data sheet to look this stuff up, to figure out how to set it up, and then you write boilerplate code to set up it up, which I'll show you here. And we're going to give that to you. So to enable, so specifically what we do is we enable the receiver and the transmitter by, the UCSR0B has 2 bits for enabling the receiver and the transmitter. So we shift a 1 into the bit position of each of those and OR them together and then set that. Now notice, by the way, I didn't OR the old value of this register. right? So if you do it this way, this is going to zero out all of the bits in that control register except for these 2 bits. It's kind of dangerous to do it that way, right? So what are we destroying by doing that? Well, this is the register. So we're setting these 2 bits, receive and transmit enable, and we're going to wipe out all these other bits. So what are we wiping out? The interrupt enable. So if the interrupts were enabled before, they're going to be disabled now. So you have to be careful when you set these registers. I'm not sure. I don't remember why I did it that way. Probably Charles was more careful than I was when he did his code. But I just put those 2 bits in there and just zeroed out the rest. Set the frame format, 8 data bits, 1 stop bit, no parity. Those settings just happen to be in control register C. So we set control register B and C there. Same thing. I zeroed out the other bits. And then to send and receive, there's UDR, which is a register you can read or write. So to send a character, this basically is waiting for, now this is an example of reading a control bit. So in the A, the UCSR NA, which is the first control register, there's a bit in there that tells you whether the data is ready or it's ready to send. So you have this while loop that just does a busy wait until you're ready to send. And then to send, you can take your data that you want to send, which would be 1 character in this case. So in this case, data is not a string, it's 1 character. And you just set it to UDRN, and that'll send it across the link, or that'll stage it to send across the link. It won't send immediately, of course, because it has to serialize it. And then if you want to receive a character, it's the same sort of thing. You can do it with a busy while loop, where you wait for the receive bit to be set, and then once it is, you just return UDRN, which is the byte you receive. So this is an example of a control register that behaves differently when you read and write it. So if I write to this UDRN and then I immediately read it afterwards, I'm not going to get the value that I just wrote, because when you read from it, you're getting whatever's coming into the UART, and when you write to it, you're sending something out, right? So it's not like the read and write behavior is different, right? Like I said, if you write to it and you read from it after, you're not going to get the same value you just wrote. Okay, so this is the boilerplate code. You're going to see this in. We're giving them this, right, Charles?
Yeah.
Well, obviously we're giving us in the slide, but this is the code that we wrote. For you so you wouldn't have to go and try to hack, and make the UART work. So this sets up the speed here. This UART baud rate is actually set in the make file. So when you compile it, the compiler has passed the -d UART baud rate equals. So this is actually this value is actually set by the make file. In case you're wondering where that's set. So that equation gets computed here. You set that control register. You enable TX-RX. You set the character size. And actually, Charles does destroy all the other bits. So he did it the same way I did it. He didn't OR this and preserve the previous state of that register. He puts. Oh no, I'm take that back. No, he has bar equals. No, he actually does preserve it. Sorry, Charles. No, he did it. He did it right. I was the one that screwed that up. So he does use, if you use OR equals, it's actually gonna preserve the previous values in there. And then he sets the character size of 8 using the C register. He sets 1 stop bit, which requires that you put a 0 in one of those bits in the C register. It disables parity. And then this is the cool part. There's a function that's in the AVR library called fdevopen. This is not something you would normally find in POSIX, but it allows you to pass a function pointer in that will tell it what to do when you print a character or if you read a character from the console using printf and scanf. So you've got this put char and get char, UART put char and UART get char, which are functions that you have to also define in your code. But you send the pointers to those functions in the init function, and those functions are essentially what I showed you before, which is putting a character has a busy while loop, and then it waits for the transmit to be ready, and then it sends the C, whatever character you want to send, to UDR0. Now there's an additional bit here that looks for a new line character in your string. If you send a new line character, it replaces that new line character with a carriage return new line. So it inserts a /R before any /N, and that's just because in UART, line breaks are handled with /R/N as opposed to just So in Unix, like if you store a string in C, you would just have a /N for a new line if you want to go to the next line. But on the console, like when you use a terminal emulator, you want to have new lines should start with the combination of /R/N. Yes.
On the previous slide for the input parameters in the bottom for the FDev open.
Yes.
Is there a particular reason they're out of order, and is there a way we can see input parameters for all the functions to know if we're doing that right?
That's a good question. Do we have documentation for FDev open somewhere?
I mean, if you search for AVR libc FDev open, they have docs online, and I think depending on how the version of Ubuntu in the university labs handles their packaging, I think if you do man free AVR and then the name of the AVR libc function, it should give you the man page for the AVR libc version of that function rather than the POSIX version. That seems to be something that's dependent on how they decided to package stuff, though. Okay, he can check. But yeah, essentially, I thought FDev open. I thought you had to give it the file handle that you wanted it to use. I thought you had to pass in std in and std out instead of null. But
Yep.
Yeah. So there you go. And if you
But it doesn't. This is all of them, though. Interesting.
scroll down, it has it.
Yeah.
It breaks it out a little bit in more detail.
FDev open.
Yeah. So there's the. Yeah. So it takes a file handle. So that would be like std in or std out or something.
Yeah, but we didn't do that though, did we?
Those are function pointers that take a.
Yeah, there's a function pointer. There's two function pointers, right? Function pointers that take a file handle. Yeah.
Yeah. Oh yeah, that's right. Yeah, because the file handle, right? It lives. Okay.
Yeah. So if you look at the definition of putchar, UART, putchar, and getchar, they do. Yeah, these functions take a character in a file stream. So this is consistent with what's in the man page, the prototype.
Right. And the reason, if you're wondering why you would want that, is that, like, for example, when you do a screen, which we're going to do later in the semester, you might make, say, standard error be the screen. So then you could do fprintf std error and have it show up on the screen, and do fprintf std out and have it show up on the console, that type of thing. But file star it's really just an integer that just keeps different output streams and input streams apart. You could have many if you wanted. I don't know why you would, but you'd have like 10 inputs if you felt like it, I guess.
Well, you could. Yeah, you could have you could have an input.
10 outputs are,
You could have an input from buttons. You can have an input from the UART console. You could have an input from. Yeah, you could have an input from, you can't have multiple inputs, sure. You can have as many as you want, depending on how you set up the board.
This totally ignores that, so this just assumes everything is you're just reading or writing to the console always, just because I wanted to keep it simple and not
Yeah.
have a bunch of extra stuff.
Otherwise, you'd have to have a conditional code in here that looks at the stream, which stream, right? Okay, so there's UART get char and put char, and then once you have those set up, then you can use printf and scanf, and they'll use the hardware UART controller on the chip. Okay, any questions about that? Everyone with me? So we're going to give you that, so that way you put that in your code, and then you can use the standard printf and scanf, or any of the standard POSIX I/O routines, and they'll go through the console. Now Charles and Philip will go over this in lab. But these boards have there's going to be two, I've got it wired up. There's going to be two USB connections The first is the programmer, which is this white box, and it connects through ribbon cable to the board, and this gets plugged in, and this is the programmer. This is the way that you program the board. You do it through this programmer device. And then the hardware UART is connected on the board between those port D, 0 and 1. They go through a chip on the board that converts that UART and drives it over USB. So there's a second USB cable that you'll plug directly into the board, and you plug that into your machine, and Linux will detect that as a UART. And then it will create a TTY for it in the dev. So there's a dev TTY USB 0, which then you can use. You can use that file and connect it to a terminal emulator. In our case, we're going to use PicoCom, which is a terminal emulator that allows you to interact with the board over a terminal interface. You guys with me? No? I know that was fast. You guys will go. They'll go over this in lab with you too. In fact, I might have time here to do it. Let's see. I've got 20 minutes. I might have time to do it right here for you. I just want to get through a few more slides first. Okay. So far we've covered how to do GPIO, at least output on GPIO. I haven't showed you an example of input yet, but it's similar. And I've talked about how to use the hardware UART, which is going to give you console access to a terminal. That basically is how you're going to interact with the board through on your workstation. The last thing we need to cover for the lab is interrupts. The chip has 26 sources of interrupts, meaning that those are events that can occur that will cause your program to stop whatever it's doing and jump to a interrupt service routine for that interrupt, assuming that the interrupts are enabled and that particular interrupt is enabled. Does that make sense? Right? So what am I talking about? What kind of events? Well, there's two external interrupt pins called int0 and int1. Those are just pins on the board that you can plug one bit into. Their inputs. So you plug a wire into them that is driven by an external device that's using the same voltage, right? And so you can trigger an interrupt when the bit on that pin goes high or goes low, right? You can make it rising edge or falling edge active, or you can trigger whenever the value goes high or low, or is high or low, right? Those are external interrupts. But then there's internal interrupts. There's 24 internal interrupts that are triggered by peripherals that are external to the processor but are still on the chip. So one of which is the UART that I just got done talking about. Instead of doing what we've got in our code here, you see we've got this while loop here. This while loop it spins. It just sits there and loops and doesn't do anything. It occupies the processor by essentially doing an infinite loop until, well, not infinite, but it's a loop that's just not doing anything until the UDRE0 bit in the USCR0A register is set. You guys with me? In other words, it's a loop that's waiting for a character to come in. It's waiting for it's waiting for the next character to be available to go out, actually, because this is put char, right? Same idea. It's waiting to put the next character out on the UART, right? The problem with this is that while you're doing that, you can't do anything else. So the other way to handle this is to use an interrupt, which allows you to do whatever you want to do. You can do other stuff on the chip. The chip can do other stuff, and then whenever the UART interface is ready to send its next character, it can interrupt the software. The software in the interrupt service routine can send the next character out, and then it can resume what it was doing, right? So that's an example. You can have interrupt for that. There's also timer interrupts that allow you to do periodic interrupts at certain time intervals, which is useful for time division multiplexing the processor, for instance. You may want to do something for a while and then switch and do something else for a while and then switch and do something else for a while, right? most of the peripherals, in fact, maybe all of the peripherals on the chip have at least one interrupt associated with them, right? Now, the problem is that, now also the nice thing about this is that every interrupt has its own vector, meaning that you can write individual interrupt handlers for each interrupt, which is actually pretty nice. Other processors don't work that way. They'll have one interrupt handler for all interrupts, and then once you get in there, you have to then check to see what caused the interrupt before you then go and do code specific to that interrupt, right? So that's called polling interrupts. These are actually vectored interrupts. So that's pretty nice. You can write, so you just write all your handlers, and then you can just assume that the code that is at the beginning of that handler is happening because that specific interrupt happens. Now, one of the things that I find a little confusing, though, is that there is a global interrupt enable, which I guess I don't have here. I have it on an earlier slide. There's a status register, which I had all the way at the beginning here of the slides. Yeah. So there's a status register. Bit 7 is the global interrupt enable. So you can turn on all interrupts or turn off all interrupts just by setting that one bit. But if you have them all on, if you have them enabled, you have that bit set to 1, then that means that it's going to enable all interrupts that are currently turned on. But the problem is that to figure that out, each peripheral has its own interrupt enable in its own control register, and it's completely non-standardized across all the control registers. So it's very difficult to get a global picture of which interrupts are currently enabled. But luckily, the board will disable all of the interrupts by default. They'll all be turned off by default. So unless you turn one on, like if you don't turn on any interrupts explicitly, then even if you turn on the global interrupt flag, you don't have to worry about the interrupt firing because they're all disabled by default. You guys with me? Okay, so let's show you an example of this. So let's talk about the external interrupt first. So we've got so there's the external interrupt mask register, for instance, is an 8-bit register. 6 of the bits are just wasted, and the 2 low order bits correspond to interrupt 0 and 1. So you can turn on external interrupt 0 or 1 in this external interrupt mask register. Okay. Additionally, you also are going to want to define in this other control register, the EICRA, you want to define what it means, like what do you consider to be an interrupt on each of those pins. And you can choose between, for each one, there's 2 bits. So there's 4 possibilities for each of the external interrupts. And those 4 possibilities are a low level. So if the interrupt 1 is a 0, that constitutes an interrupt. Any change, any logical change can constitute an interrupt. Or you could do falling edge or rising edge. Okay, so let me give you an example here before I run out of time. Okay, so I want to set this up. I want to take the board. I want to have a button, and when I push the button, I want it to trigger the interrupt, the external interrupt. That's going to allow me to. This is going to give me a lot of flexibility because I can have this thing, I can have the processor doing whatever it wants to do, and whenever I hit the button, then it can go and it can acknowledge that I hit the button, right? So I've got the board here, and I'm going to take this pin 2, and again, you wouldn't know this unless you look at our diagrams or find it in the data sheet. But if you look over here at this pin 2, see how it says, I don't know if you can read it in the back, it says interrupt 0, interrupt 1. So if you go to the lower lower right-hand corner of the board again, and you go up 3 pins, that's interrupt 0, and the next one up from there is interrupt 1. So that's why I'm going to connect the button to that pin. Yeah. So I'm going to take one side of the button, I'm going to connect it to pin 2, and the other side of the button I'm going to connect to a 3.3 volt 1, right? Now, I actually screwed this up when I first did it. I thought the button, when you push the button, I thought it would short I mean, okay, there's 4 pins on the switch, right? Why do you need 4 pins? You need 2 pins. You have 2 pins. When you push the button down, it connects to 2 pins, and when you release the button, it disconnects to 2 pins. Why is there 4 pins? I don't know. But I assumed that the top and the bottom pins were the ones that were shorted when you push the button, but I don't think we have any documentation for this button either. So this was just trial and error. There's no instruction sheet on the button.
Well, I mean, there's only 2 possibilities.
Right, and I, of course, picked the wrong one. The first. So anyway, it turns out it's horizontally, so the left and right side are connected. So I set it up like that. So when you push the button, it's going to short pin 2 to VDD, basically, right? And if you release it, pin 2 will be floating. It won't be connected to anything. So I was thinking, well, okay, if you push the button, it goes from floating to high. That should look like a rising edge to the chip. So to set that up, and this is pretty cool. It's pretty simple. You set up the service routine by typing ISR and then int0_vect. Now where does that come from? That you only know from looking in a header file. There's a header file, which yes, this header file. Userlib AVR include AVR IOM328p.h has all the vectors. So as I mentioned, there's 26 vectors. Each one ends with _vect. It's usually pretty obvious which one you want. So I used int0vect, and then I made that a function and said, I just put printf push button, right? So this is assuming that I've got the board connected to the UART as well, right? So I can do it. Otherwise, printf won't do anything. You guys with me? Okay. Okay. So now you might say, well, what? I don't recognize this syntax. This is a macro.
Yeah.
It's just this is a define. It's not really. This gets expanded out to something else once the preprocessor runs. Okay, and then in the init function, well, I mean, I assume this is the init function because I had an init function that I showed you earlier for the UART. You could just have this at the beginning of your main function as well. I set the interrupt 0 to be rising edge sensitive, which is at EICRA. Notice I used the binary constant here in C, which starts with 0B, so 0B11. And then I turned on, and again, I just blew away the rest of the bits. It's probably not good form, but this would zero out the other whatever the other interrupt was. Then I turn on the int0 interrupt by setting the EI mask to 1. And then I enabled all interrupts with SEI. So SEI sets the global interrupt enable in the status register. All right. And then, well, I don't show what I have after this, but it could be anything. It could just be a while loop that just an infinite loop after this. This just sets up the interrupt. Once you've got the code running, then whenever you hit the button, it'll press button. All right. So that's a really simple way to set that up. And obviously, you might say, well, that's kind of trivial. Well, we're going to obviously build on this and use this to build more complex systems. Okay, and then there's also timers on this thing, which are really versatile because you can use timers for time division multiplexing the processor, but you can also use them for performance counting, like as a cycle counter, if you want to check how many cycles it takes to run a section of code. So and they're also used for the pulse width modulation circuit as well. The problem with the timers is that there's 3 timers. They can count up or they can count down, but one of them is 16 bits and the other 2 are 8 bits, which is really kind of problematic because if you're counting every cycle, then you're going to fill up an 8-bit counter, in a really small amount of time. Same with a 16-bit counter. But there's a ways you can get around that, which I'll show you. So the timers also have these I think they each have 2 control registers, A and B. There's TCCR1. Timer 1 is a 16-bit counter timer. It has this control register that allows you to set it to increment every clock cycle. So you don't divide the clock. You can have it tick up once every 8 cycles or 1024 cycles, but I set it to 1. This is if you wanted to set the 1024-bit prescaler, but I actually set no prescaling on this one. So I'm sorry I'm rushing. I want to get through this last example before we run out of time. And then yeah, that would be if you wanted to overflow at 1 second. You could initialize the counter. So the counter is going to roll over at, after it gets to 65,536, it's going to roll back to 0. But you can pre-initialize it so it'll roll over after a second. So there's 16 million clocks per second, but if you use the 1024 prescaler, you divide it by 1024, and you subtract it from there. So you can initialize the counter so it rolls over at a certain amount of time. That's one way to use these things. But I have another example that uses it for something else. So let me show you that. So I wanted to come up with this way, a little game where I'll have a light, and the Arduino, the Atmel processor will wait a random amount of time, and then it will light up the light, and then you're supposed to hit the button, and it will measure what your reaction time is, how fast you were able to hit the button after seeing the light come on. That's it's like a little reaction time, how quick are your reflexes type game. So for this, I've got the button wired up as before, but I'm also going to add an LED. So I take an LED, I'll stick that on the board. I'll wire that up to as a GPIO pin over here on PD4, I guess. 0, 1, 2, 3, 4. Yeah, 4. So I've got one side on the LED and the other side on ground. Okay. So I'll set up the interrupt handler. So when it gets an interrupt, the button interrupt, it'll disable the interrupts. It'll set a global variable called press button to 1, and then it'll print button interrupt. And then I have another timer interrupt, another interrupt here that's for the timer is whenever it overflows. So it's a 16-bit timer. You will not be able to hit the button fast enough to have it not have the odometer on that thing roll back to 0, right? Because it'll happen within 65,536 divided by 16 million. It's a very small amount of time. So I set up an interrupt to keep track of the number of times it rolled over. And I store that in a 16-bit variable, global variable, which effectively will turn this counter into a 32-bit counter. If you concatenate those number of overflows, and you concatenate that with the actual timer when you hit the button. So I declare those down here as uint underscore, well, the button press is uint8, and the overflows is a uint16. And then the main program loop is super simple. It just says, it prints wait for it. And then in order to make it wait a random amount of time, you just generate a random number with rand. This is a standard POSIX function, rand. It works, it's part of the AVR lib. And while the random number that you generate is greater than a constant, which I call probability to go, P to go, it'll just keep looping, and every time it loops, it'll delay for 1 millisecond. So there's another function, the built-in function, delay millisecond. Once it gets past that, it'll say go, and then it'll reset the counter. It'll reset the overflow counter. So this is the 16-bit counter. This is effectively the low order 16 bits of the counter, and this is the upper 16 bits of the counter. It'll set the LED to 1, so it'll light up the light, and then it'll enable the interrupts. And then after it does that, it'll initialize push button to 0, and then it'll wait for the push button to go to 1. And I might say, well, that's never going to happen. It will, because this is a global variable that'll get set to 1 in the interrupt handler for the button, right? So even though I'd be stuck in this while loop, the processor will escape from that while loop to respond to the interrupt request, because I have an interrupt handler for that. And that press button is a global variable. And you can just keep polling that, essentially. And then once you get past that, you turn the LED out, and then you do some math here to calculate the 32-bit value, essentially concatenate the overflows with the counter value, and then you print out your reaction time is and give it the number of cycles. So it's a pretty neat little game, and you can see it doesn't require that much code. Okay, so that's all I've got for today. Oh, that worked out perfectly. Now, one thing I didn't get to is I didn't get to the lab description yet. So we're going to be assigning Lab 1. It's on Moodle, and let me just show you that real quick.
And remember, we do have lab this week, so you should come to the lab. Make sure you figure out who your partner is. You already said that.
Yep.
But do come to lab. It's happening.
So if you go to Moodle, you'll see we've got the first lab is assigned. There's a project skeleton, which the TAs will talk about that and how to set that up. Also, the lab sheet is there, and I want to call your attention to handouts too. We've got some handouts. Everything listed under the handouts section we wrote, and the stuff that's under reference material is stuff that other people wrote. The handouts section has a prerequisite lab I mentioned last time, but there's also an AVR programming guide, a section on UART, talks about the background of UART, mostly the stuff that I talked about today, but it's in written form here. And there's a C programming guide for those of you that aren't comfortable with C maybe, because you're more used to Java or Python. So there's a nice introduction to C there. And then list of system requirements for the hardware if this is something you wanted to set up on your own machine. But we have everything required in the lab.
Is in the lab